to motivate our idea, we consider the most simple case. We consider find minimum or maximum of this function, two variable function under constraint. The constraint is gxy is 0. So how to solve this problem? So geometrically, gxy equal to 0 is a curve, represent a curve in R2. Then if say is f x0 y0 is the wanted minimum, constraint minimum, that is a point z x0 y0 here. This is the point x0 y0, and the value of f at this point is c. Okay, and this c is a constraint minimum, which means the value of f at this point is minimum among all values of nearby point on the curve g equal to 0. Okay, so we consider the curve f equal to c, maybe fxy equal to c. This represents a curve. This curve is f equal to c, right? So geometrically, you see that if we increase c a little to obtain another nearby curve, so the intersection of the nearby curve, which the curve g equal to 0, is a point near to the x0 y0, but the value of the new corresponding c for the new curve is maybe we decrease c a little. It's smaller than the original c. So this c could not be minimum. Okay, cannot be the constraint minimizer. Okay, so when will this c to be minimum? It is not difficult to see that only when the curve f equal to c is tangent to the curve g equal to 0. Only point like this can be the constraint minimum. Only point at this position. So that is you draw the curve of g to be 0. Maybe I will draw so this is g equal to 0. So then you for many say, for every say you have f bc1, f bc2. So given a say you have a curve f equal to c. Let's say values you have many curves. So this curve and also this curve. So only this, when the curve f equal to c is tangent to g equal to 0, that is at such a point can be the constraint minimizer or maximizer. Okay, because in the case where there are no tangent, you can increase or decrease c. For your xy, keep your xy in the curve g equal to 0. You can decrease your c or increase your c. So such a c will not be a constraint minimizer or maximizer. Okay, so only when the two curves f equal to c and g equal to 0 are tangent, you can obtain your constraint minimizer. So when it is tangent, what happened? when it is tangent, they have the common normal vector. The normal vector is coline, is linearly independent. So if the gradient of g at the point x0, y0 is not 0, we must have gradient of f x0, y0 be linearly dependent of the gradient of g, that is lambda. They have the same direction. This means the normal has the same direction, means that the two curves are tangent at that point. They have the same tangent line. Okay, so it turns out that this condition is suitable to obtain to solve the constraint extreme value problem. Okay, and this condition does not involve solving some variable by the other. So this is more manageable in applications. Okay. So in general, we have the following theorem: Lagrange theorem. French mathematician. Omega is an open set in R, M, and f is a function defined on omega, C1, continuously differentiable. G is a function also defined on omega, but it is a vector valued function, Rn, and M is the zero set of G. Okay, so upon M, if G, the component of G is J1, Gn, then this M is precisely G1, X1, Xm, B0, Gn, X1, Xm, B0. Okay, so the set M is the constraint set. It is determined by n equation of M variable. So the M is a subset of Rm, determined in this way by n equations. But of course, if you use the vector value function, this is simply Gx to be 0. So this is the setting of our theorem. If x0 a point in M is a minimum point or maximal, that's okay, of this function, we consider f, we restrict our f to the set M. Okay, so this is omega. Our set M is here. Omega is the domain enclosed by this curve, and M is a curve in this picture. So we consider f as a function on M. Then x0 is a point in M. X0 is here. Okay, so if x0 is the minimum point of the function restricted to the constraint set M, so what happened? We also assume that the rank of the derivative metric of G at x0 is n. Then the conclusion is that then there is a lambda, n-dimensional vector lambda, such that the gradient of f at x0 plus the gradient, the transport of lambda multiplied the derivative of G and x0. This is 0. So this is the conclusion. Let's have a look on the final result. This result means that firstly, the derivative of g and x0 is an n by m metric, and lambda, the transport of lambda is 1 by n row vector. Therefore, the multiplication of lambda transport and g point g x0 is an m-dimensional row vector. The gradient of f and x0 is also such a vector, so we can add them together. So the conclusion is that we can find a suitable lambda so that this is 0. Okay. And so in application, we will use this result to help us to find the minimal point x0. But the lambda is also not known. X0, the m coordinate of x0. X0 has m coordinate, so m unknown number, and lambda has n coordinate. So we altogether has m plus n unknown. M plus n unknown. But we only have an m equation. Because this equality is a vector m-dimensional vector equality. So this is m equation, m scalar equation. But we have m plus n unknown. The number of unknown are more than the number of equation. But we need to remember that gx0 is also 0, because x0 is a point in M. So gx0 is 0. This provides us another n equation. So in fact, we have m plus n unknown, x0 and lambda. Altogether are m plus n unknowns. But we also have m plus n equation. The first m equation is the conclusion of the Lagrange multiplier theorem. That is the conclusion of this theorem. And we still have another n equation. That is the constraint condition. So it is reasonable to solve this m plus n equation to get the m plus n unknown we want. Okay. So this is the Lagrange multiplier theorem for constraint minimum extreme value problem. Okay.